Okay. Well, thanks all of you to this meeting. I appreciate it. It's great to know some new people in Summit County. I actually live in Silverthorne myself. And a little bit about me and my history. I have been in academic science for since 1985 is when I started my first job. I basically have a PhD in chemistry, but I have become more of a biologist as time went on. And my research program has really been focused on the molecular events that cause cancer to develop. And then more recently, looking at how some of the changes that we see on a molecular level also affect certain developmental states and diseases and the ability of cells to develop into the kind of, how do you say it, adult cells that they need to become as we go through development. So I started my career at the University of Southern California as an assistant professor. And then about 28 years later, I moved to Baylor College of Medicine. I still have my last PhD student to graduate, so I still am affiliated there. But in the last 2.5 years, I came to work and be the president and CEO at the Keystone Symposia. And one of the drives that I had for doing so is the fact that they share a very special passion that I have had my whole career, and that is supporting this next generation of a scientific workforce. When I was at USC, I served a lot of different academic administrative roles. I was the associate dean for our graduate programs in the medical school. I created new graduate programs for PhD students. Coming to Baylor, I was the dean of the graduate school there, where I oversaw almost 2,000 students and postdocs in the biomedical sciences. And Keystone is really, really passionate about being inclusive and promoting the success of these young investigators. So what I'm going to do today is give you a little bit of an idea. Many of you, or if not all of you, have not, except for Woody, who used to be working at the Keystone Symposia as well. Most of you probably know nothing about it. So I thought it'd be good to get you seeing what we do because it's part of your community, and tell you a little bit about who we are. Let's see if I can share my screen now.
Yep, we can see that.
Yeah. Okay. Let me see. I'm going to have to. Okay, great. Okay, so the overall mission of the Keystone Symposia is really to ultimately accelerate the way diseases are diagnosed and treated in a general sense. So what we do is we actually catalyze the advancement of biomedical and life sciences by essentially connecting scientists together within a particular field and even across fields at conferences and various workshops. Many of these, as you'll see in a minute, are held at venues across the globe. And the whole idea is to bring these individuals together to allow conducive informational exchange, generating new ideas, connect people that wouldn't normally connect with each other to, again, accelerate the science and the research. So we were founded in 1972, which means next year we are going to be celebrating a big milestone, our 50th anniversary. And the initial Keystone was in the LA area, out of UCLA, but we moved shortly after those first 5 or so years, I believe, Woody probably knows better, to Keystone or the general Keystone area. We are a nonprofit organization, and the way we are funded is through registration fees from our attendees that attend our meeting, as well as corporate, foundation, and individual donations. We have a staff that are about 40 or so right now. They're full-time, and then we also have part-time or seasonal employees as needed to be on site for our conferences. And I think by many accounts, we're considered the premier global biomedical research conference organization in terms of the quality of what the science that is being presented, and the quality of the sites and the venues that we use. We generally hold about 60 meetings a year in our conference portfolio. They start usually in the fall and go till the end of June, which is the end of our fiscal year. And we are very committed to, as I said, next generation of scientific leaders. So diversity in a very broad sense is extremely important. Diversity in terms of career stages, gender diversity, global diversity in terms of participation with other countries, and of course, racial and ethnic diversity as well. Again, the scientific presentations are of utmost quality. We've had over 100 Nobel Prize winners that have participated in our conferences to date. And the nice thing about our conferences is they're not huge. So that allows a lot of intimate interactions between attendees. And it ranges, depending on the topic and so forth, between about 150 and 600, with an average of about 225 or so. And in a normal year, we essentially bring in to our conferences about 14,000 individuals. Also, really importantly, is being able to bring in people from different countries, different perspectives into our conferences. So having this global reach is very important. Since I think it's about 2000, where our conferences have been held in at least 64 geographic locations, 19 countries on 6 continents. So that's important, not only for people to come to the US in our meetings, but also for us to bring the science as well to these different continents and countries. And as you'll see in a minute, we have a very broad range of topics that are covered in the general biomedical and life sciences landscape. So this just shows you a map of where our conferences have been held. Largely, as you can imagine, a lot of our conferences are held in the US, and many of them are held here at the Keystone Resort or at Beaver Run. And as we talked earlier about what's going on in terms of vaccinations in Canada, which is looking pretty bleak, we have a number of sites in Canada that we're hoping to be able to convene conferences in at these sites that we've used quite extensively in the past, starting in January. So fingers crossed for that. As far as the topics, this gives you some snapshot of the different areas that are represented in our conference portfolio. We have, it's an ever-changing mixture of conferences that we offer. And importantly, they're not all the same. In other words, if we're talking about cancer, there's different aspects, for example, that will be portrayed in the conference programming in different years. One mainstay, of course, is cancer immunotherapy, which is a huge thrust of work that's being done for therapeutic efforts. We have, besides some of the topics that are always represented, like cancer and immunology, for example, in our conferences, we have new conferences or new topics. In technologies, for example, we had the first meeting in digital health that we had pre-pandemic. So we're always looking at emerging areas as well as areas that are doing very robust science to include in our conferences. It's a really unique program as to how we build the conference portfolio every year. Many conferences, people will come, scientists will come and say, I have a topic that I think we should have a meeting on. And then they develop, the speaker list and so forth. We have, in contrast to that, a very rigorous process by which we decide which meetings are going to be held in the portfolio for that coming year. And it starts with our scientific advisory board. We have 100 individuals, again, from all over the world that are represented, high leaders, high quality scientists and leaders in these different categories of scientific topics that we bring together. And we do it twice a year, January and June. And we meet in person, at least again, pre-pandemic, we meet in person, and they are divided up into study groups, if you will. And these individuals will take all of the proposals that have been put together that we ask our initial study group to provide online. And there's hundreds that come in online. And then those particular proposals are selected, which are the ones we want to go forward with. And then the scientific advisory board whittles those down to decide what are the main topics that we're going to put in our portfolio. They also suggest who are the best people to organize it, looking at, again, diversity, who's presented before, who hasn't been, an organizer in the past. And so they make suggestions. We reach out to organizers. Then they come back in June when the organizers have a program that's been put together, and they critique it. Are these the right sessions? Are these the right individuals? Do we have enough diversity in career stages, et cetera? So it's a very deliberate and thoughtful process. And then for the meetings proper, we basically have a number of what we call plenary sessions. And these are the invited speakers that we have coming to the meeting that were designated by the organizers. And then in addition to that, we have smaller talks, what we call short talks, that are selected from people that present an abstract on the research that they want to present. And they can present if they get selected for that short talk, or they can give a poster presentation. So what's really important is, besides just having talks all the time, is that we have a considerable amount of unscheduled time, usually in the afternoons, for informal networking. And, basically we found that informal network really develops new collaborations and interactions, young scientists that get to engage with leaders in their field. In some ways, having been to one of these meetings when I was young, it's like you're going to the you're going to some big gala where you meet all the stars that you love, and this is really, I think, a really empowering experience for these young scientists to come and not only present their work, but they can also see who the leaders are in the field, get to know them, and in some cases they get new positions or new jobs. So that's important for us. And then, as I mentioned, besides some of the topics that are reoccurring every year in our portfolio, we have a number of new topics each year, and that's directed by our scientific advisory board, that we think this is the cutting edge of new areas that we really need to form a community of sorts and get them together. So this is kind of what it looks like, a little bit of a disarray, but it's very fun. On the left, you see a coffee break. In the middle, you see one of our talented graduate students that came to our meeting that's presenting her poster. And then the right just shows you the interactions that occur in the poster sessions. And I found it interesting when I first came, many of our staff are not scientists. And I would say, how did the meeting go? And they'd say, it was great. And I said, well, how do you know it's so great? And they'd say, the noise on that poster session was so loud. There were so many interactions that it was great. So, so those are quite fun. So one thing, as I said, that's really important for us is to support this next generation. And in doing so, we provide a lot of different opportunities for career development. So we started what I call a roundtable forum, where we have a group of panelists that introduce themselves. And then what they do is break out into roundtables of about 8 to 10. And then students and postdocs, these young trainees, will talk to them about specific issues, that they might want some more information on, Or how did you do this in your career? What did you think was the most important decision you made, and so forth. We also, again, are very committed to enhancing the diversity of speakers, attendees, and these workshop leaders. And we're looking at beyond what we do as an organization in terms of conferences, how can we best support careers of these young individuals? And we created a program, again, that's relatively unique, we call it the Keystone Symposia Fellows Program. And basically it brings individuals that are in their early stages of a career that really need some support and help into this program. It's a year program, and they're able to come to our 2 yearly SAB meetings and engage with, again, top scientists in a variety of different areas. And we have, or I have monthly meetings with them that we look at different types of skill sets that we're looking at developing in these individuals to, again, foster their success and have them confident to go on as future leaders. So COVID-19 has obviously had a big impact on us. We had to very abruptly cancel roughly 28 conferences between and then between September and December, we had 10 conferences there that we also canceled. So that was a major impact. However, with that and the significant reduction in revenue loss that we experienced, in addition to the cancellation for some of the sites, the penalty fees of the sites that we were going to use, we decided to be very proactive and aggressive about keeping the science going on. So challenges that we had really created some interesting opportunities. So what we did is starting in June, and I should back up, we canceled one of the most important conferences that we now know would have been the worst one to cancel. And that is, we had a conference scheduled to be taken place in Florence, Italy last March, with Tony Fauci as the keynote address. And so, you know, the idea of trying to cancel these very timely conferences, we decided we have to turn to doing virtual events. And so we've done, I think, an amazing job converting our whole operation from in-person meetings to virtual meetings. The positives that we've seen, and I think this is the big silver lining, is that we've been able to charge much less for registration. People don't have to travel, so there's an eliminated expense there, and they don't have to stay in a hotel. And this has really allowed a substantial increase in access for young people and investigators from low and middle income countries that couldn't possibly have afforded to come to our meetings. So I think that's really a positive. Again, decreased time and expense required to attend a conference. And as I said, the science must go on. We have to continue, particularly in this time where there's so much needed to understand this pandemic, COVID-19, and therapeutic approaches. The negatives, of course, are there's less of this spontaneous networking opportunities, although I think we've made a tremendous progress in optimizing the best we can to create that sort of forum or by different formats in our conferences. There's some concern people have presenting unpublished data, because that's in essence what we aspire to, is having people that will present stuff that's not published in the literature, so you get the latest and greatest results. And of course, time zone accommodations, when we're looking at, you know, people that want to come from Asia or India and a variety of other places, trying to balance that time zone so that as best as possible, we can get everybody during some waking part of their time frame. So this is just a snapshot again of the e-symposia that we took from two meetings. One of them was actually facing COVID-19 and other emerging infections, as you see on the left. And then the other one was Jim Allison, who presented a talk at one of our first e-symposia following the vaccinology one, That was done in August. And he, again, is well known. He's a Nobel Prize laureate for his work in cancer immunotherapy. So again, I think one of the really important things that we're looking at going forward is the ability to democratize science. And so far, we still have a number of meetings left to go, the end of May and in June. So far, we've given access, free access to 7,000 or more early career investigators and those from low and middle income countries to attend our virtual events. So what is the future of our conferences? Of course, I think for the most part, many of us are dying to get back into in-person meeting events. But I think our eSymposia virtual events are here to stay. There will certainly be a cadre of them in our conference portfolio going forward. And hybrid meetings is what we're looking at. And those are in-person meetings plus the ability to attend through a virtual streaming contest. And in that case, we have the ability to keep the people that couldn't come to our meeting in person to have access to our meetings while being able to still provide an in-person event for our events. And what we're doing is we're going to try about 15 of them next year with the hope that going forward, all of our meetings can eventually become hybrid events. As I mentioned, we're going to be 50 years old next year. I wish I was 50 still, but anyway, we have a campaign going forward, and this is going to be our first really big campaign to create an endowment that will not only be able to sustain the organization, but allow it to really thrive and grow in the kind of directions that we want to see. The three areas that we're looking at cultivating gifts are in these categories, as I show here: advancing diversity in the biomedical sciences, emerging minds, which is to support, again, young people to come to our meetings, and then the emerging topics. These are the new topics and meetings that that we put on. They generally occur at a loss, so that you know, we have to be very careful about how many of these we can convene. But I think being able to sustain that and even grow these emerging topics, this is really important. We had one of the first HIV meetings. Some of the work on cancer immunotherapy was the first to be presented in a conference through our organization. And that is really, really important to keep us all on the cutting edge. So here are the proposed topics for the Senior Center. We came up with this list, although it's a work in progress. So these are some of the areas that we're thinking about in terms of engaging either myself or Thale Jarvis, who's our CSO, or Woody, and also thinking about other people in the scientific community that we know that would be available and interested in providing some insights on these topics. So I'll stop there, answer any questions. That's my email if you have any questions whatsoever, and here is our website.
Well, thank you so much, Debbie, for introducing Keystone Symposia to the Summit seniors. To me, it's just an amazing resource right here in our county. And as she pointed out in that last slide, there are a number of really pertinent life science topics that we'll be tackling in these quarterly meetings with Keystone Symposia. So we'd open it now if anybody has any questions for Debbie. Thanks for including that slide, Debbie. I appreciate that.
Sure. Oh, I can go back to that because I went through it quick.
Yeah.
Are there any questions I can answer?
I'm looking at the chat. I don't see anything. I did have the question for you, which you are just showing on this slide. We had a question come in and say, what exactly are you going to talk about? So anybody else have any questions for Debbie?
Just to let all of you know, although we haven't been in the office for a year, where our office is located is where First Bank is, just on the side between, I guess, Silverthorne and Dillon. We're on the second floor of that building. So you can always stop by and say hi if you want to.
Well, good. Philip, are you seeing any questions come in anywhere?
I am not.
Okay.
No one has unmuted themselves, so no.
Okay, well,
Excellent.
if anything comes up, please let me know. I'm more than happy to address questions or let you know a little bit more about what we do and certainly how you might be able to help us.
Yeah, and
I'm
Philip,
sorry, I take
yeah.
it back. I do
Yeah.
see a question. It's
Literally.
coming. It's I'm going to go ahead and
it's probably from
unmute
Mark.
yes, I think so. So I'm going to ask you to unmute Mark and ask your question.
Oh, he's not unmuted.
There we go.
There we go.
Yeah, I was wondering, because I've seen, being a physician and stuff, how many conferences do you have actually here in Keystone?
You know, I'm not quite sure the actual number because it varies from year to year, but I'd say in this sort of Summit County area, because we also use Beaver Run, it's probably about maybe 10 to 15, I want to say. So there's a quite a large fraction of our meetings at the Keystone Resort, and then a few at Beaver Run. Mm-hmm.
All right. Are any of those open to the public in the sense of people within the community who are science-based or have been in their previous careers, but might have an interest in attending some of the topics that pertain to what their prior career was, or to something they're highly interested in?
Yeah, that for sure. I think we have no, how do I say, no constraints on who can come to the meeting. You have to go through the registration process. And, you know, to be honest, I'm not quite sure how many people have attended that are physicians or people that just want to come to meetings, but there's certainly no constraints. And if you would like to come, that would be great. Let me know and we'll see how we can work that out. But yeah.
Well, I guess one other question in that, because you can pick it up. I mean, if you go to your site, to the Keystone Symposia website, it has a list of the conferences, I assume.
Exactly. Yeah. So it has a list of the conferences. You can look at the conference list by discipline, by date, whatever. You can look at the and we have the January, February, and so forth meetings already on the website. And the ones that we're doing this fall, I think we have somewhere between 8 to 10. It's still in the process of being developed that are still going to be virtual events, the e-symposia. But as of January, those conferences are all going to be in person. We have 51 of those that are going to be convened. So yeah, go to the website and see. Usually there is the program comes a little bit later after the title of the meeting, but you get an idea from the abstract what's going to be presented in that particular meeting. And many of them are 3 days. Some of them are 4, but in general, they're generally 3-day meetings.
Good. Well, great question, Mark. Yeah.
Thank you.
That's excellent. Okay, looking at the time, thank you, Debbie. I think we'll move on to Woody. And Woody, if you can unmute yourself, and Philip will get you in the crosshairs on the video, and away you go.
Sure, and if Debbie could
stop sharing. Yeah. There you go.
Okay, you ready?
Yeah, we are. Yeah.
Absolutely.
Okay, so my name is David Woodland. As you might gather, I was born in the UK. I did my PhD in West Germany and then a postdoc at the National Jewish Center in Denver. I then established a research lab looking at pulmonary infectious diseases at St. Jude Children's Research Hospital, and then became president and director of a research institute in New York called the Trudeau Institute. And then, of course, as Debbie mentioned, I worked at the Keystone Symposia for a short while. I've served on many private and government boards, especially those that regulate granting. And I've served on the National Science Advisory Board for Biosecurity. That's an important board that regulates how really dangerous pathogens are regulated and handled in the laboratory. And I've also been editor-in-chief of a journal called Viral Immunology for a couple of decades. In fact, I just gave up that recently. And now I run a private consulting business. So I'm going to share my screen. And hopefully you can all see this. Let me know if you can't. So what I'm going to talk about is, in a very broad way, the science behind pandemics, basic science behind pandemics, and of course with some emphasis on COVID-19. And I'm going to address all of these questions on this slide, specifically, why do we get pandemics, what affects their severity, and some of the basic science behind COVID-19. And then I've been asked to touch on vaccines too. So the first question was, were we expecting a pandemic? And the answer to that is a resounding yes. And I like this quote from Edgar Marcuse at the University of Washington. He said, the pandemic clock is ticking, we just don't know what time it is. And he said that back in 2006. And when I gave talks on pandemics in the past, I used to liken it to the earthquake in Los Angeles. You always know that a big one is coming, you just don't quite know when it's going to hit. So why do we think this? The answer is simple. Humankind has constantly been impacted by pandemics. They've occurred again and again and again. And I've just got a few examples here, just sort of to illustrate that fact. A famous pandemic is the plague of Justinian, which started in 550 AD, spread across the Roman Empire, and probably was the final death knell to the Roman Empire. You're probably all familiar with smallpox, which was a horrific disease. And I just put this picture here just to sort of illustrate how bad pandemics can be. But it's estimated to have killed about 1 billion people worldwide. But fortunately, it's one of only 2 viruses that humankind has completely eradicated. And so we certainly don't have to worry about smallpox anymore. I just mentioned that the earliest case of smallpox was from 1157 BC, from the tomb of Ramses V. Sounds like he died of smallpox. You'll have heard a lot about Spanish influenza in 1918. It's kind of analogous to the COVID-19 pandemic that we're in now, but it's estimated to have killed about 25 to 50 million people worldwide. And then there are 3 ongoing pandemics. These are pandemics other than COVID-19 that are happening right now. One is the human immunodeficiency or HIV pandemic, which causes AIDS. It's killed upwards of 40 million people worldwide. It suddenly appeared in 1981. Tuberculosis is also considered to be a pandemic, and it kills about 1.5 million people a year. Interesting fact about TB is that about 1/3 of the world's population, which I don't know is about 2.5 billion people, are infected with a mycobacterium that cause tuberculosis. And the big threat from TB, of course, is that there are extremely drug-resistant versions of the mycobacterium that are emerging. And then African swine fever, this is actually a disease of pigs, emerged in 2018, or the current pandemic started in 2018, and it's caused pig farmers to slaughter about 25% of the world's pigs to try and stop it. We're desperately trying to keep it out of the United States. So clearly pandemics happen all the time. And this slide perhaps illustrates that better than ever. So these are data from the last 40 years. So these are recent data, and they show examples of emerging and re-emerging infectious disease in the red and blue dots. An emerging disease is a disease that basically wasn't present before and now emerges and becomes a pandemic. A re-emerging infectious disease is one that was already present in the human population at a low level, but then suddenly became much more prevalent. So there's a couple of features I want you to take home from this map. First of all, there are a lot of dots on this map, considering this is data from only the last 40 years. And the second point is that these dots are not just congregated in Africa or the Far East, but they're also in South America and North America. So everywhere is a potential site for the emergence of a pandemic disease. And I'll just highlight a few examples of these. HIV, of course, I just talked about. It suddenly emerged from Africa in 1981. And as I mentioned before, there have been about 40 million deaths from this virus. Hantavirus pulmonary syndrome is another one, and I highlight this because this emerged in the United States, sometimes called the Four Corners virus because that's where it first appeared. In an outbreak that occurred in 1993, 24 people were infected and 12 died. And there's always a fear that these hantaviruses are going to become pandemic. So far, it hasn't happened. And then there are the influenzas. Influenza is known to cause pandemics on a relatively regular basis. The last one was in 2009. It fortunately was pretty mild. It was the swine flu that emerged in Mexico. But there have been many other examples of influenza viruses that have threatened to become pandemic over the last 40 years. And you might be familiar with, for example, the H5N1 influenza virus, which is referred to as the bird flu. But so far, those influenzas have not generated a pandemic, but they always threaten to. And then we had a near miss 6 years ago, a virus called Zika virus, which is normally prevalent in Central Africa, suddenly started infecting people in other parts of the world, predominantly South America. And this was infecting pregnant women and causing the babies to be born with encephalitis. And there was a huge panic about it. And then mysteriously, this disease has kind of vanished. It's actually still present, but has dropped down to very low levels for reasons that we don't understand. But it was a near escape. But then we've had several other near misses and then a hit with a class of viruses that we never thought would be likely to cause pandemics. And these are the coronaviruses. And the first of these that emerged in 2003 was severe acute respiratory syndrome virus, or SARS. That was followed, and that was emerged in China. And then that was followed by MERS, or Middle Eastern Respiratory Syndrome coronavirus, which appeared in Saudi Arabia in 2012. And then finally, we had SARS-2, which emerged in Guangdong province in China, and that caused a pandemic that we're all suffering through right now. So I want to talk a little bit about these coronaviruses because it's really interesting and illustrative of how pandemics work. So this is the third topic. There are 3 new human beta coronaviruses that have caused significant disease in humans over the last 18 years or so. So these are enveloped positive strand RNA viruses. And the only thing you need to know about that is RNA viruses are relatively unstable, which means they can mutate very rapidly. The name coronavirus means crown, and here's a micrograph, electron micrograph of a coronavirus. You can see the surface is dotted by these spikes. This is actually the spike protein, and it looks a little bit like a crown. That's how these viruses originally got their name. So as I mentioned, there have been 3 coronavirus outbreaks over the last 18 years. So this first one, SARS-CoV-1, emerged in 2002. It was characterized by very high pathogenicity, had a case fatality rate of about 10%. But fortunately, it had low transmissibility. There was an outbreak in Hong Kong and another outbreak in Toronto, and the virus threatened to go worldwide. But because of this low transmissibility, it never quite was able to transmit enough to cause a pandemic. But it was certainly a near miss. And then in 2012, MERS-CoV emerged in Saudi Arabia. This is very highly pathogenic. It's got a case fatality rate of about 34%. This is on a par with smallpox. So it's highly pathogenic, but it has very low transmissibility. Unfortunately, it hasn't yet learned to transmit from person to person, but this is certainly on biologists' radar to follow. And then, of course, in 2019, in Wuhan, we had SARS-CoV-2 emerge in 2019. And this has medium pathogenicity. It's got a case fatality rate around about 0.1 to 0.3%. That's on a par with seasonal flu, but it's very highly transmissible. So it spreads very easily from person to person. And this is why this virus of the 3 was finally able to elicit a pandemic. So why do we get these pandemics? What's going on? And the answer is quite simply zoonosis or zoonoses. So the animal kingdom is rife with viruses. All sorts of animals harbor lots of different viruses, most of which are specific for those animals and don't infect humans. But every now and then, one of those viruses can transmit to a human, learn to live in that human, and learn to transmit. And then you get a pandemic because you have a huge population of people that can now be infected by this virus, which is new to that population. And these are sort of examples of that phenomena. I've talked about HIV. This actually emerged from chimpanzees, which harbor a similar virus called simian immunodeficiency virus. Hunter pulmonary syndrome virus is a mouse virus. It's secreted in the droppings turn to dust, and then people can breathe that in, and then you can get this Hunter pulmonary syndrome. Influenza virus is actually a bird virus. There are lots of different types of influenza that infect predominantly waterfowl, and the virus lives in their guts. But that virus can transmit to pigs and then sometimes to humans, and that's how we get pandemic strains of influenza virus, which are distinct from the seasonal strains. Zika virus is a monkey virus. It's transmitted by mosquitoes. And then the two coronaviruses, SARS-1 and MERS, are definitely bat viruses, and they're transmitted via an intermediary animal. And in the case of SARS-1, it's probably a civet cat. And in the case of Middle Eastern respiratory syndrome virus, it's definitely camels. So camels are the main animal now that are transmitting that to humans. So what happened then with SARS-CoV-2, which caused COVID-19? Well, it certainly is a bat virus, and so it is probably transmitting between bats and not causing much of a disease in those animals. It then is probably transmitting to some other animal, perhaps by biting them. And that process probably happens many times before the virus finally learns to live in that animal. And then if that animal is in close contact with humans, you can start getting transmission to humans. So that can happen, for example, in a wet market. And then the virus can adapt. Once it's infecting humans, which is probably a rare event, it can start adapting and then learn how to transmit from human to human. So there are several key adaptive steps that have to happen. First, the virus has to learn how to bind to human receptors in the lung. Second, it has to learn how to get into the human cell. And then once it's in the human cell, it has to learn about that particular environment, that physiology, so that the virus can work in that environment. And then it has to learn how to spread human to human, which is when you finally trigger the pandemic stage. So we know that a couple of, or 2 or 3 mutations had to happen for this change to occur. So this is a picture of the spike protein, remember, that sits on the surface of the virus. So it's sitting on the virus membrane. The white is actually the protein of the spike. And then all this fluffy stuff on the outside is sugar, which basically coats the protein and tries to protect it from the immune system. And it binds to a protein on the lung membrane called ACE2, angiotensin converting enzyme. So that's shown in red. So that's how the virus is able to stick to the lung membrane and then cause an infection. And we know that some mutations had to happen because initially this system is not set up to infect a human cell. So the first mutation that happened was that there was a mutation in the spike that allowed it to bind much more tightly to this red ACE2 molecule. So this mutation probably occurred when the bat virus was infecting its intermediary animal. And then once that happened, the virus had to learn how to actually infect the cell. So the interesting thing about this spike protein is that it's under tension, and it's like a tightly coiled spring, and it can be cleaved by an enzyme called a protease. And when it's cleaved, it unfolds dramatically and essentially injects the genetic material of the virus into the lung cell. So the human didn't have the right protease to cut the spike protein. So the virus had to make a mutation in its spike protein to allow it to be cut by a human protease. And then that allowed the infection of the human cell. And then, of course, additional mutations occurred on top of that to allow the virus to increase its transmissibility between humans. And we know that there was probably a significant mutation that happened in the European version of the virus that really accelerated transmission of this particular virus. And there was a huge outbreak in Europe early on. So that's how the virus learned to get into humans. So what are the factors that affect pandemic severity? Well, we know that viral mutation is one. I just talked about that. We know that exposure to similar virus can affect how the pandemic develops. The size of the susceptible population is a big factor, and then vaccines, which I'm going to touch on. So I'm going to touch on each of these. I did mention about mutations, but you're probably aware of the mutations that are circulating right now. The main ones are listed here in this diagram. And the United Kingdom one is characterized by an ability to spread more rapidly. The South African variant also is able to transmit much more readily. And in this case, it also appears to be more resistant to the vaccines that we have. And then we have the P1 in Brazil, which I think spreads more rapidly and is resistant to vaccines. And we're also watching variants in the United States, the California and New York variants, both of which are probably significantly more transmissible than earlier variants of the virus. So that affects the course of the pandemic because this allows the virus to spread more rapidly and maybe to evade natural immunity. The second factor that can affect a pandemic is exposure to similar viruses. And there's an interesting story here with regard to coronaviruses. So it turns out there are 4 coronaviruses listed here that cause the common cold. So I don't know if you know this, but there are over 200 virus strains that cause the common cold. And 10 to 25% of these are coronaviruses. So they have these weird names. So all of us have been infected with these viruses, and we may have some level of immunity to them that will be cross-reactive to some degree with the SARS-CoV-2 that causes COVID-19. So the impact of a SARS-CoV-2 infection on any individual may depend on how many times they've been infected with these cold viruses, how recently, and so on and so forth. So these existing viruses in the human may be affecting how the pandemic is developing and who gets very sick and who doesn't get very sick. I might add that each of these coronaviruses may have started as their own pandemic historically. We were just never aware of it. And then the last point is the size of the susceptible population. So I mentioned that seasonal influenza and COVID-19 have similar case fatality rates. COVID-19 is probably a little bit higher. So why are we much less worried about seasonal influenza? And the answer is that most of us have been infected with influenza, probably relatively recently. And if you've been infected in the last 6 years, you're probably immune to flu. So if you look at this big blue circle, you can imagine this is the population of the United States, which is what, 330 million people. And probably if the people that have had flu in the last 6 years covers about 80% of that population. And then if you look at the number of people that have been vaccinated, you find that covers an additional another 10% or so of the population. So the number of people that are actually susceptible to flu each year is only about 10% of the population. So if we have 330 million, that's 33 million people are susceptible with a case fatality rate of 0.1%, then that's around about 33,000 people dying a year. And that's actually what we get with seasonal flu. COVID-19 is different, of course, because when this pandemic arrived, no one was immunized. Because there was no vaccine. And although there were these cold viruses, they were not inducing protective immunity. And so there were 330 million people that were susceptible. And with a case fatality rate of, say, 0.3%, that means about 1 million deaths. And we're actually on a par to perhaps reach that number eventually. So the last thing I just want to quickly touch on are the vaccines, because vaccines, of course, definitely impact the course of the pandemic. So the goal of a vaccine is to elicit immunological memory, that's protection against subsequent exposure to the pathogen. In other words, a vaccine tries to trick the body into thinking it's seen this virus before and to have strong immunity against a second infection. And there have been about 230 COVID vaccines that are either in development or have been approved. And they're kind of listed here. And they're all different types of vaccines: nucleic acid vaccines, protein-based vaccines, which are just the protein of the virus, inactivated or weakened forms of the virus, and then viral vectors that bring in information to generate immunity, and bacterial vectors that do the same thing. So there's been many different types, but there have been two real major successes in vaccine development. And these are the mRNA vaccines, Moderna and Pfizer, and then the non-replicating adenoviral vector vaccines. As you know, it was AstraZeneca, J&J, Sputnik V, and CanSino are the leading examples of those. So I'm going to talk about these. I'll start with the adenovirus ones. So the adenovirus COVID vaccines were generated by these companies. Gamaleya is the Gamaleya Research Institute in Russia that generated Sputnik V. Janssen is a subsidiary of J&J, and CanSino is the Chinese version of all of these. In this case, the vaccine is based on another virus called an adenovirus, which causes the common cold. In fact, there are about 88 human adenoviruses that cause the common cold. And they're all listed here. So we've all been infected with these. And the idea is to take one of these viruses, make it so that it can't replicate, and then put on that spike protein from SARS-CoV-2 to generate immunity. And this turns out to work very well. So the AstraZeneca company uses a chimpanzee adenovirus to avoid any immunity to human adenoviruses. It uses the same virus for the prime and the boost, and it's 70% effective at preventing illness, and it's 99% effective at causing severe disease. So it's really a good vaccine. The Sputnik V is similar, except it uses two different human adenoviruses. And it's claimed to be 91% effective, although I don't think anyone's really seen the data on that. So the great thing about these vaccines are they're really easy to manufacture en masse. They're inexpensive. It's only $3 a dose. They can be stored at room temperature as a freeze-dried powder. But the negatives are that they're difficult to modify when new COVID strains emerge, as is happening. And as you're probably well aware, there are very rare but potentially severe side effects from these vaccines. So the second class of vaccines that have been really successful are the genetic vaccines. And this involves an amazing new technology. So you have to sort of understand a little bit about how genetic material is translated into a protein that can do functions in the body. So we all have DNA, and the DNA encodes proteins, but that's all trapped in the nucleus, and all the protein production is done in the cytoplasm. So you have to get the information from the nucleus into the cytoplasm. And the means to do that is by this messenger RNA. Basically, a copy of the DNA is made with this nucleic acid called mRNA. It moves from the nucleus into the cytoplasm. And there's a huge enzyme complex called a ribosome, which can read that sequence and turn it in. So there were many attempts to make vaccines just using DNA. The idea was put the DNA in and you'll get the protein that you want, in this case, spike protein, and you'll have a vaccine. But it turns out that never worked in humans. So the second approach was to use this mRNA as an alternative. But it seemed to be very problematic because mRNA is very unstable. It degrades very, very quickly. It's also inflammatory. But fortunately, there was this scientist, Caitlin Kariko, Hungarian biochemist actually, who kept working on this. And she was told many times this would never work. This was a useless approach. And in fact, when she was in the United States at the University of Pennsylvania, she was not promoted to full professor. And I know that she had enormous problems getting grants. But it turned out she was right. And she's made this particular approach work. And I think this lady's in line perhaps for a Nobel Prize. But it also illustrates the difficulties that women have in science. And this is something that Debbie mentioned, that diversity in science is really important, and Keystone Symposia is working really hard to make sure that women get a fair shake in science, which is not the case today. So these new mRNA vaccines have been produced by Pfizer or BioNTech and Moderna. They basically just encode the SARS-CoV-2 protein, so that it's produced in the cells of the muscle. And they're 95% effective. This is extraordinary. These are some of the most effective vaccines ever. Oops. And they're 99 to 100% effective against severe disease. The problems with them are that they're challenging to produce and they cost about $20 a dose. They're difficult to transport because they need to be stored at very cold temperatures, and they require 2 shots for full efficacy, which is not true of the J&J adenovirus vaccine. But the one very positive thing is there are very few side effects, perhaps just allergies in a few cases, that's all. So let me quickly summarize what I've said. So pandemics have repeatedly affected human populations. New and old pandemic pathogens constantly lurk in animal reservoirs, and the transmission from animals to humans is being exacerbated with their increasing encroachment on wild animal habitats. Pandemic severity is impacted by several factors, such as the rate at which the virus can mutate, pre-existing immunity, population susceptibility, and then lastly, vaccine availability. The medical community did an amazing job of developing these novel vaccines in record time. They were generated in about a year. It normally takes a decade to make a new vaccine, so that was amazing. And the bad news is we're likely to suffer more pandemics in the future, but the really good news is that I think based on the experience over the last year, we're going to be able to respond much more effectively and develop vaccines, for example, in a much more timely fashion, even than we did in this pandemic. And with that, I'll be happy to take any questions. And thank you for listening.
Thank you so much, Woody. I mean, I've seen this once before, but I still learn new things. That was just amazing. Thank you so much for educating us.
Thank you.
We have a couple of questions that were posed when people signed up, but I don't see anybody in the chat. So, but raise your hand, anybody, if you have a question, but I'm going to go ahead and ask Woody a couple of the questions that were put in on the online sign up. One person asked, how do you determine the length of efficacy of vaccines, and how do you modify vaccines to account for variants? I think you answered at least the second part of that a little bit.
Yeah, so those are good questions. So durability is an important issue with vaccines. If you vaccinate someone, how long are they protected? Obviously, the longer, the better. The question, though, is how do you determine that? And the answer is there is no way to determine it other than to wait and see. So we won't really know the durability of these new COVID-19 vaccines until time passes and we see how people's protection persists or wanes or whatever. So if it wanes rapidly, we'll have to generate people will have to have second shots, booster shots, maybe every year, like in the case of influenza. So that's certainly a possibility. On the other hand, they may last for a lifetime. We just don't know, especially for the mRNA vaccines, because those are just so new. And the way you modify the vaccines is you have to rebuild the vaccine to be effective against a new variant, because you have to change the spike protein to match the new variant. That's relatively easy for an mRNA vaccine. It's much more difficult for an adenovirus vaccine. But the challenge is always then testing those new vaccines. That's what takes to generate a new mRNA vaccine probably takes a day, but then to test it takes months of time.
Excellent. One of the other questions, I know Dee Dee is on the line here. What is and I know you're not a medical doctor, but she would like to know what would be the opinion of receiving the vaccine after completing infusion and radiation for lymphoma?
Yes, I should stress I'm not a medical doctor, and the best person to answer this question is her doctor herself, because that doctor will know exactly what the state of the patient is in terms of their immunity and so on and so forth. But in very general terms, vaccines need to have a strong immune system in order to generate strong immunity. And if someone has a weak immune system, it's harder to generate really strong immunity. So that's always an issue. It's more difficult to vaccinate elderly people because their immune systems are weaker. That's why many of us get the stronger version of the flu vaccine every year rather than the standard version. And of course, if you have some kind of immunosuppression because you're being treated for something, that also can impact how well a vaccine will take in that individual. But this person should check with their own doctor because it's obviously a very personalized decision, very specific to the circumstances of that particular patient.
Okay, and then we had one last question in the online. Is there any evidence that the COVID-19 virus is transmitted by touching surfaces? How about transmitted by people outside, walking or biking? If we wear a mask at a gym, will we be safe? So it's sort of a couple of questions in one.
Yeah, so I think the general consensus is COVID-19 is not that easily transmitted through surfaces. I remember at the beginning of this outbreak, some of my relatives were getting their groceries and leaving them in the garage for 2 days, or spraying them with nasty chemicals before using them, which is obviously not a good idea. The fact of the matter is that in order for the virus to transmit from a surface, it has to stay moist, and most viruses desiccate very rapidly. So they last a very short period of time on any kind of surface. So if someone sneezes on a door handle and you immediately go and grab that door handle, then yes, you could transmit the virus. But in general, surfaces are not really a big problem. The virus is transmitted by aerosol, by people sneezing into the air, and then those fine droplets are spreading and people are breathing them in. And this is almost certainly the main way in which the virus is transmitted. And in fact, it's very similar to what happens with influenza. And we know a fair amount about transmission in the case of influenza. Now, the issue about people walking outside or biking, obviously, if there's a lot of air movement, which there would be outside compared to an indoor environment, it's much harder to catch COVID-19 when you're around people, just because the conditions are not ripe for really passaging a lot of virus from one person to another. Indoors is a bit of a different story because the virus is trapped and you're breathing the same air, you're recirculating that same air again and again. So that's why the guidance has always been when you're outside, it's much safer than when you're inside. And of course, the question also said asking about wearing a mask at a gym. So obviously that depends on whatever the local guidance is for that. But to be safe, it's always better to wear a mask. The mask is better at protecting other people from being infected by you rather than you being protected from infection yourself. But to the extent that masks help, you should wear masks if you're worried about COVID-19.
Good. And Phil, do you want to read off David Hicks' question? Or I can read that if you're muted. A question in the chat. There was an early discussion about challenge testing to speed efficacy studies. Any update on that approach for future needs?
Yeah, so a challenge study is a study where you actually infect someone with the virus in question, and then you'll take people that have maybe been vaccinated or not vaccinated and just see how does it work. These are not popular studies because they're very problematic. You're effectively infecting someone with a pathogen. And in the case of COVID-19, you're infecting someone with a potentially very dangerous pathogen, because even if you don't die from COVID-19, there is a possibility you can have long-term effects. And so I know there were some challenge studies that I think were being done in the UK, and I think they were proposed in the US, but I don't know that those were ever followed up. Debbie might know, yeah, I don't think those are ever followed up. It's basically too dangerous, and there are other ways to get the information that we need.
Yeah, I'm quite sure there hasn't been anything on that.
Interesting. No, I would not want to be part of that study. Thank you very much.
Well, you know, early on, there was a feeling that COVID-19 You know, in some people it caused, in elderly people, it could be lethal. But then in younger people, it wasn't so bad. That was kind of the early feeling about this. And so I think that was when these challenge study ideas were first being floated. And, you know, you might have been able to get people in their 20s, maybe 30s, to volunteer for that. But it's since become apparent that COVID-19 has very long-term effects. My wife and I had COVID-19. We had effects for 3 weeks, but I know that some people can have effects that last for many months. So it's definitely a virus you do want to get.
I think the take-home message is it's very unpredictable. Generally, people that don't have comorbidity situations, you know, if you have it, that's a bad thing. But the ones that seemingly healthy can die from it. And that's the problem, is we can't yet know what it's going to take in terms of a person's innate immune system or a response to the virus that's going to protect them or make them more susceptible for severe disease.
So we do have a question from Mark, and he's unmuted.
So, Dr. Wood, I guess my question, it's more of a comment too, is, so you made the point that we've eradicated smallpox by mass vaccination of all populations, and we were able to, or they were able to get that done throughout the world. It took a worldwide effort. You couldn't just do certain countries. COVID, we've been able to get ourselves to level green here and level clear, and we have 70.7% of, or 9% of our population in the county vaccinated. But we have not eliminated COVID, or still haven't even eliminated measles and things. My question is, or to the point of the anti-vaccinators and the people who are refusing to be vaccinated, or just the hesitancy to vaccine, especially with the mRNAs, which have been exceedingly safe. Do you have any comments about what the effects of all this anti-vaccination hysteria is? I mean, when we were all of my generation, at least, we all had to get, we started getting polio shots and everything when they first came out. We got measles back, well, a number of my generation had measles before the vaccines and things.
Well, yeah. So, I mean, you raise a really good point. So there's a few factors at play, and there's actually a lot in your question. I show that picture of a child with smallpox. I sometimes get into trouble for that because it's shocking. But I think people have to realize some of these diseases that we used to encounter regularly were horrific, really horrific. And what's happened is we've done such a good job with public health at basically eliminating most of these diseases that we're in a period of hubris where people just don't understand how lucky we are to be protected from so many diseases. So then they begin to forget, well, actually it's vaccines that are doing this. And so I think that's the main thing, that people have just forgotten how valuable vaccines are. And that will change when we stop vaccinating people for whatever reason and some of these diseases come back. Smallpox is eradicated. By the way, the second disease that was eradicated is rinderpest, which is actually a disease of cattle. Excuse me, I'm sneezing here. And both of those were eradicated by a very strong vaccination strategy. But there's a couple of features about those viruses, and that is to the host. So smallpox only infects humans. It doesn't infect other animals. Similarly, rinderpest infects certain cloven hoofed animals and nothing else. So that makes it easier to eradicate. And that's why we might be able to eradicate polio. It doesn't infect any other animal species. The problem with SARS-CoV-2 is it infects other species. In fact, cats can get it, dogs can get it. So our attempts to eradicate it from the human population will probably never be successful. So what's going to happen in the long run is that the virus will adapt to the human population. It will become like flu. We'll probably get a vaccine against it, maybe every year or maybe every several years, depending on the durability of the vaccines. And we're just going to have to live with it. And people who are not getting vaccinated simply increase the length of time until we reach that status quo. And that's unfortunate because people will die. If people are not getting vaccinated and we continue to have relatively high levels of infection, more people will die. If everybody would get vaccinated as soon as possible, that would save a lot of lives. But yeah, I've spoken to a lot of anti-vaxxers over my career, and it's very difficult to get the message through because they're concerned about the side effects. And there are always a side effects with vaccines, of course.
But I think to a large extent, it's a lack of education, right? I think somehow, you know, I've heard things like people are not getting vaccinated because they don't know what's going to happen in 2 years after they get the vaccine. And so educating them that the immune response is the same for all these vaccines, independent of the delivery process, right? And so that's one thing. And then the other issue is, I think, particularly for this one, there's a lot of concern about it was developed too fast. Mm-hmm. And as Woody and I both know, this was, yes, this particular sequence of mRNA and this technique was developed quickly, but in terms of for specifically the coronavirus. But this type of technology has been in play for a very long time in terms of the development of the particles, for example, that house the mRNA. All of that has been developed over years. It's not that it was, you know, started from scratch. So there's a lot of misconceptions, and I think trying to educate people and also giving them, you know, the idea that, you know, where is your greatest risk, right? What do we know and what do we don't know? And, you know, some people will say, well, I'm not going to get this, or I'm still young and I don't have that much risk. But then they're willing to take that risk with the idea that they've made up some story that something's going to happen in 2 years, and because they got this vaccine. So I think the key is trying to educate people in as simple terms as possible, so they don't see this as something so foreign and therefore they get really scared. The anti-vaxxers, that's a little bit of a different issue to me, because they have a different maybe premise about the problem with vaccines in its entirety. But I think for this one in particular, I think that's really, you know, a big part of it is just fear of what's going to happen down the road.
Well, there's a lot of misinformation out there, and you
Yeah.
can online and you can find all sorts of information, and a lot of it is just nonsense. But for the average person, how do they know what's good information, bad information? And that certainly is where the education piece could really come in.
So you're saying we need to do a better job with our public health and our politicians and everything regarding education of how the vaccines work and their true benefits.
Yeah,
I think it can't be politicized, like it, you know, whether you look at it from the mask perspective or anything. Just getting the actual facts and having the politicians, healthcare experts really have the same message, if you will, and educate people in a way that they understand what's to lose. And it's, you know, many people look at it very selfishly. You know, I don't want it. I don't want to risk myself. This is a humanitarian effort. The more people, it's a race, right? The more people that refuse to get vaccinated, the more hosts that virus can replicate, make mistakes, and cause these mutations that cause more people to get infected easier, potentially more lethality. And so it's not just their situation that they need to look at. They know that this is something that's going to benefit humanity.
I mean, it's not, I 100% agree. I mean, I've been a big vaccine proponent in this county in the recent drive, but The other question I had, and so I just wanted to see what your comments were. The other question I had for Dr. Woodland is that we mentioned that, you know, the biggest problem with making vaccines is not that the technology isn't there, but the time it takes to get them, to test them and get them approved. But we can change our influenza vaccines basically on a yearly basis, looking at what's occurring in other parts of the country or the other hemispheres first, and then predicting what might occur in our hemisphere. How is that done so rapidly? Because they're using the adenovirus or another live virus or attenuated virus to give it. They're not using mRNA.
Yeah, so, well, so flu is a very special case. It's a seasonal virus, comes predominantly in the winter. And of course, in the northern and southern hemispheres, winter comes at a different time. So, and the virus mutates at a steady rate. So what happens is that the people that make influenza vaccines basically go down to the southern hemisphere in our summer and their winter, and they look at what vaccines are circulating. And then they develop the vaccine around that so that it's ready for our winter season. So they take advantage of this difference in seasons and the different hemispheres. And the vaccine itself, most influenza vaccine is what we call, it's either subunit or killed virus. So it's not an adenovirus or anything like that. It's not mRNA. It's made basically by killing the influenza virus and then sort of putting that into a vaccine and just giving you the protein. It's a pretty weak vaccine. It doesn't work particularly well, but it works just well enough to give some degree of protection to most people. And because they do the same thing year after year, and because the processes are the same year after year, they're able to do that in about 6 months. Sometimes they're a little late, sometimes you'll hear that, and sometimes they get the choice of the actual protein they're going to use wrong. And so sometimes you'll see there are delays in the influenza vaccine, or you'll hear the vaccine doesn't match perfectly. But it's because they do that on a yearly basis that they're able to do it so quickly. There is one live attenuated version of the vaccine. It's called FluMist, and that is, you can get FluMist in some places. So that's a live influenza that replicates very slowly in the nose. It gives you strong immunity, but it doesn't give you actual influenza. But most of the vaccine, as I say, is actually either killed virus or protein.
Well, thank you, Woody. I'm looking at the time and I know you have a hard stop very quickly here. So I'm going to draw this to a close. Thank you so much. Debbie has already signed off. We so appreciate your information. And I know for one that I know a lot more than I did when I signed on. So thank you so much.
You're welcome.
All right.